This is the second video of a two-part series looking at I2C in-depth working with our MCP9808 temp sensor. In this video, we create our own library and use the particle debugger with our Xenon. In our library, we not only will provide the basic operations of reading a temperature, but also implement the alert capabilities of the chip, which will interrupt our Xenon if the temperature moves outside the range we've set. By providing this functionality, we now have the capability for our Xenon to sleep longer and only wake up when it's triggered by this alert. Alright, so in this video we are going to program our Xenon to work with the MCP9808, but we're going to add some capability that the standard library doesn't provide, and that is the ability to set the upper and lower limits of an alert so that we can go to sleep, and if the temperature exceeds those limits, it'll wake us up and we can pull a new reading and send that reading. And this is also an opportunity to use another capability that I'm really excited about, which is the debugger capability with the Particles ecosystem. So as you can see here, I have the debugger, which has the debug chip, and it also has a cable, and the cable is a JTAG and also supports single wire debug to the board. And it is keyed, so I can pop this into the connector there, and then the USB is going to go into my USB bus here. And the other thing to keep in mind when we connect this is that we're going to also need the standard USB connected. So when I first started using the debugger, I thought that the JTAG would be all that I need, but it turns out that for whatever reason, the way this is working, we are required to have both connected. So keep that in mind when you set yours up as well. And the reason I want to use the debugger in this scenario is because when we start working with the registers to do the setting of the upper and lower limits of the temperature, we have to do some math to kind of move some bits around and do some things to set them properly. And the debugger is a really helpful capability to have us jump through that code and really see what's going on and debug it. And that I will show as a part of the video. Okay, so before we get started, I just wanted to talk about a couple things related to the debug capability in Particle Workbench. First of all, currently it is in beta. And so we've still got some rough edges that still need to be worked through, but they're updating very frequently, which is good to see. And we're hoping that we'll be out of beta soon. The second thing is that currently there's only something called a monolithic build when it comes to using the debugger. And that's a little bit unfortunate because not only does it increase the amount of time that it takes to download the application onto the target, but it is also optimizing the code. And optimizing the code is really not what you want to do to a certain extent when you are debugging, because it kind of throws the debugger off. So we'll look at that as well. And so despite these issues, I still think that it's relatively usable, and so we're going to jump in and use it. So here's a graphic sort of looking at these optimized builds. So in our normal build process, we have our device OS and our application, and these two are actually built separately, and they're actually downloaded. The device OS goes down to 30,000 hex, and the application goes down to D4,000 hex. And what's nice about this scheme is once you put the device OS down there, whenever you're making changes to your application here, you don't need to rebuild the whole thing and send the whole thing down. You're just rebuilding and sending down the application. And we can actually see that down here. So when I go to clean, for example, I get a choice to just clean the application or clean the application and the device OS. And notice that it doesn't break the two apart for the debugger. It just says clean application for debug. And then over here on the right, when we're going to build, of course, we have compiled just the local application, or we can compile both that's what we would do if we've cleaned both. And of course, we can compile for debug, which is going to do the monolithic compile. And the same thing for flashing. So when the debugger is executed, what it's doing is putting all of this stuff together. So it's one big monolithic build, and it all goes down to 30,000 hex, and we, move forward in that respect. So just keep that in mind, that this is a little bit of a limitation right now. My goal, or my hope, is that we'll get to a point where we'll be able to set the optimization off on the application, but keep it on the device OS. If we did this monolithic build with optimization off, which you can kind of go in and hack it and make it do that, the application is too big to actually fit on the target. So unfortunately, that's not an option for us right now. The other thing that we're going to cover in this is an introduction to C++ classes. Now, because my YouTube channel is sort of taking you beyond Arduino, the likelihood is you've already been exposed to C++ classes, but I just want to do a quick review and some of the things that I find are sort of the big rocks, at least to get started. And one is how to declare it, the actual implementation file for what's declared in our specification, if you will, what the private and public sections are, those will be important. How to create a constructor, that's always important when you start out. The pragma once, which is kind of a cool pragma that gets rid of this if not defined stuff that you'll see a lot in libraries, and we'll point it out as we go through the code. And then, of course, how to include it. So the first thing is, let's just look at declaring a class. So in this case, this is a class that's being declared for the MCP9808. And essentially what we've done is really created a new type in the system. So just like there's ints and floats and booleans, there is now an MCP9808 type. And the implementation of that type is actually what we're going to create in this class. And so we would say type, and then my sensor, give it a name, and we now have a variable that actually points to this class. So the class is the template, and this is actually creating the object from the template. Now, when you declare a class, one thing you're going to want to include at the beginning of each class in the header file, which we'll get to, is this pragma once. What this does is it protects the class from being declared multiple times. And it is a case in C and C++ that you can include this in many different places, and it can end up including it multiple times, and you don't want to do that. So it's kind of a hack, if you ask me. More modern languages protect against this automatically, but in the case of C and C++, we need to do this manually, and we do this by adding the pragma once at the beginning, and then we don't worry about it after that. And then in this section here, we're showing a private and a public section. So we have private int I2C address, and we have public, and then we have some function here that we want to make public. The concept here is that things that are in the private section are not visible outside the class. So even though you declare an object of a particular class, you are not going to have visibility to this variable. And I'm putting an underbar here as just a convention. It doesn't need to be there. These names can be whatever you want. But with an underbar, it sort of can be a visual indication then when you're coding and developing that this is a private variable and not a public variable. When we look at the next part of this is to create constructors. So in our public section, if we declare a function called MCP9808, basically it matches the name up here, and then we give it an argument or set of arguments, then these arguments can get passed at the time of creation. So for example, we can say MCP9808, we give it a variable name, and then we say equal, and then we name the class again, which is actually naming this function as the constructor. And then in this case, because we've given it a default, so this I2C address is at 18 hex, we don't need to resupply it here, so we can leave it out, or we could supply it. The other thing is that now that wherever this is being declared, it has to have visibility to this class, which is usually in a header file. So you're going to have the #include MCP9808.h at the beginning. Then we have to actually implement the constructor. So the way we implement the constructor is to do the name of the class : and then the name again of the class, which is the name of this function that we declared here. And then we can provide the argument. And then when we pass this in, we can say underbar I2C address equals I2C address, which is what's being passed in. And we can do a wire.begin as well in our constructor. We do whatever we want in the constructor. But at this point, we can fire up the two-wire interface or I2C because that's what we're going to be using. So that would be a logical set of things to do in the constructor. Finally, on the public side of things, here's public, so we still have our constructor here, but now we're going to declare another function. This function returns a Boolean, takes no arguments, and it answers the question as to whether we're connected to the sensor or not. By the way, you'll notice here there is no void here, so this is a very telltale sign. The fact that this matches, it doesn't have a void or it doesn't have a return type, shows that it is a constructor. So down here, what we would do for that is we would just go into our file, add in a Boolean, MCP9808 is connected, and then we would put whatever code we wanted for that. So what's interesting is as we accumulate all of our functions here that they're going to be able to call, every time we add one, we're going to want to create an implementation for it, and we do it with this syntax by renaming the class : and then adding the function name. One other thing, just as a cheat sheet, which I'll have as a link in the show notes, is bit manipulation. So we do a lot of bit manipulation when we're doing firmware development because a lot of the devices that we work with registers, and all of these registers have specific meanings, and even the bits have specific meaning. So for example, if I've got something that's set to hex 38 and I want to basically shift this left 4 bits, I can use the 2 less than signs with a number and that will shift it left. And of course, if we did that, it would end up being hex 80. Or if I want to shift it right 3 bits, I can do that and it's a 7. A common thing is I need to just set a bit and I don't want to change any of the other bits. So what you can do is start with a 1, tell it the number of bits to shift left as an example, and then OR it into the value. And by doing that, so you're going to start out with 0001, and then it'll shift over 6 points, and so it'll have this new value. The 1 will be moved, everything else is 0. So when you're ORing in all of these zeros with a 1 in one spot, then it's not going to affect the other bits, but where the 1 is, obviously it's going to get set. And then the reverse for clearing is basically start out like you're setting, but then do a NOT, which basically turns all the zeros to 1s and the 1 to a 0. And then when you AND it in, it will cause that 1 bit to clear if it's set, and the others, since they're ANDing with 1, are just going to stay the way they are. And then finally, if you wanted to clear several bits at once, you can just set your mask to whatever it is and then do an AND operation as well. And then finally, toggling bits. So if it's a 0, it's now a 1, 1 to 0, rather than going through the if then else logic, you can use the uptick equals, and that will cause it to flip. So with that, I think we can jump into the code and we'll start writing up our library for the MCP9808. And the key here is that we're going to add some new functionality to be able to set the thresholds for an upper bound and a lower bound so that we get an alert if the temperature exceeds or goes below those thresholds. Okay, enough talk. Let's start some coding. So the first thing we're going to do is create a new project. I'm going to do it in the same folder that I've done my others. We're going to call this MCP Alert. And we now have our new project, and of course we have our template source file, which is very helpful for a lot of people, but I think we're past this at this point. I'm going to just delete it and put down my favorite way to start, which is basically to say that I want the device OS to be a separate thread in the operating system, and I want to do a manual start of the wireless network and the radios, and we're not going to use them in this video, so manual is perfect, so we're not wasting time jumping on a network or jumping on the mesh network unnecessarily every time we download code. So this is how we start. The next thing we want to do is do a clean application and device OS. This is always good practice when you first start out. And then we're going to set our configuration for this particular project. Configure workspace for device. We're going to do 0.9 and it's Xenon. And the name doesn't really matter in this case, the way we are doing things, but we'll put a name in. So you'll see down in the bottom right here, the little red flame. When that goes away, you know that everything is set up and ready to go. And then what we want to do is, let's just do a compile application and device OS because we cleaned everything, and we'll do an initial build. So this will take a little time to finish. So I will fast forward through this big, large build, and we'll pick up shortly. Okay, so we've gotten a compile for the device OS, so now it should jump into our application, and we are done. And although this can be somewhat painful first time out, I like to do this because I know I have a good, clean compile and everything is ready to go in the project and nothing is weird. So I've got a good starting point. So now what I want to do is start working on our C++ class. And to do that, we're going to create a new file called wclMCP9808.h. And then I'm going to create another file called wclMCP9808.cpp. So I'm doing WCL in front of it for Windy City Lab just to differentiate it from the standard library. And when we finally make this a library that we want to submit up to Particle, we can differentiate it easily, and we don't have any name collisions. So in the .h file, what we're wanting to do here is start out with our pragma once, because remember we said every time we declare a class on the header file, we want to have that in to stop it from pulling it in more often than it needs to. And then we're also going to do this include application.h. And what this does is it actually brings in the entire Spark framework, which is really almost identical to what you would have in the Arduino IDE. And so that is necessary as well. And then finally, we've got our class. So the next thing we want to do is really go through the datasheet and add in all the pound defines that are necessary when we start doing our coding. So what I've done here is these actually came from the other MCP standard 9808 library. So I'm just going to reuse those. But essentially what we've done here is every register with their number is being identified here. And we don't want to be using these numbers in our code. We want to be using these names so that it's easy to see what we're doing and debug. And then these are the masks. So these masks that they've created are a little different than the way I discussed in the slides, which is you give it a bit number and then you'd shift it over and then set it or clear it based on that. Here, they've already done that with the mask, and then you use the mask. So that's fine. That works. Then the next thing we want to do is add in our private and public section. So we have a private section here, and then we're declaring this I2C address. And we're using an underbar here, again, just to signify that it's a private variable. And a uint8t is basically an unsigned integer that's 8 bits wide, and underbar t just means it's a type. And then we come down here to the public section, and we have wcl MCP9808. So this is the same name as this, and this is where we're creating the constructor, and we're giving the constructor a parameter, which is an address, so that we can, when we do the constructor, we could give it a different IP address if we've set the A0, A1, and A2 pins to, something different. Okay, and then let's go actually create our constructor. So we've created the specification for it. So we're going to go into our CPP file here, and we are going to add this call. We are going to add this signature, if you will, where we have the class name, : the actual constructor name, and then our actual implementation. Now this is giving us a bunch of flags because we actually haven't included the .h file. So we can do that here. And once we do that, then it should see those declarations and then those errors go away. So what we're doing is we're bringing in an I2C address, which here is set to a default value. And then it comes in here, it gets assigned to the private variable, and then a wire.begin is how we fire up the I2C interface. So one other thing we can do is declare another function here that's public, and we'll put it here. And this is going to be a function called isConnected, and it's going to return a Boolean. And so what we can do is then go back here to the body, if you will, and add the code in for isConnected. So we've added this in. It's saying that this is incompatible with the spec. And the reason for that is if we go back to the .h file, we see here that it's returning a bool, but the code that I pasted in here is returning an int. So these have to match. This whole thing here has to match exactly with what is here, with the exception of the default being passed. So now that we get that corrected, we don't have any errors. And then what isConnected is doing is it's basically starting a begin transmission on the I2C address. It's going to write out the register, which is register 6, and then it will end, and then it'll do a read. So now the MCP9808 knows which register you're wanting to read from when you do the read. We wait till we get 2 values into the buffer, into the I2C hardware, and then once we get it, we do a read, shift the first most significant byte left 8 bits, do another read, OR it in, and we should get this value here. So we're almost done and ready to start trying some stuff. I want to just add in the rest of the functions that we're going to implement. So we're going to implement the set upper temp, lower temp, setting a critical temp, and we're going to set the alert itself by enabling it or disabling it. And then we also want to set whether the active or the alert pin is either active high or active low. And then we're going to have a Boolean for alert status and a float with get temp, which will get us the temperature. So at this point, we've got enough code that I want to try some stuff out. So let's go back to our main function here. And what we want to do is include our MCP, WCL, and then we will actually declare a variable of this type. So we can say WCL MCP9808. We can call it temp sensor. And then we want to use our constructor that we created for this, which we get there, and we will not pass anything because the 18 default is fine for our I2C address. So this declares it. Then the next thing we can do is say we want to check to see if we actually are connected. So we could say while not temp sensor dot is connected. And essentially what should happen here is that we'll go into this. If it doesn't work, we'll never get past this. So it will constantly return a false. Which, by the way, if I go back here, these should also be returning true and false. Okay. So I'm going to just hit build here, compile the application locally, and let's just make sure that we do get a good compile. And we do. So that's good. So now we have our temp sensor declared. We are going to check to see if it is connected or not. We're using the constructor to actually initially construct the object, and then we're going to call the isConnected. The constructor has been written here. All we're doing is setting the internal I2C address with what's being passed in, and we're firing up the I2C interface, and then we're going to go through this isConnected. So what I want to do to try this out is I want to use the debugger to actually see how this works. So let's do that. So what we're going to do is go over here and click on this little bug, and we are going to pick this. So over here, there's different ways you can interface with different hardware. We're interfacing with the Argon, Boron, and Xenon, so that's what we want to pick here in the drop-down. And then I'm going to click Debug. And I have already put my device in DFU mode, which is why it just said there wasn't anything there now, because I'm already in DFU mode. So what should happen is we're jumping in here. We're going, notice how big the file is now. So we're back up to, almost 660K. And what's going to happen next is we should start downloading this to the board. And again, you can see the board size, or the size of the image is rather large. So this, takes a little bit of time. Okay, so this would be typical of what you would see when you first start out with the debugger. So the debugger is actually stopped, and as you can see up here, we can start running by clicking on the run, but I want to set some breakpoints first. So the first thing I want to do is go over here, and if I hover just over on this line and I click that red dot, I've created a breakpoint, which is listed down here. And now if I hit run, I am going to run, and it actually stops on the first breakpoint. Hooray. I mean, that's awesome. So this is right where we should be. But what I want to do is I want to go into the isConnected here, and I want to actually step through this and see what happens. So what I'm going to do is I'm going to come down here, and let's set a breakpoint on line 14, because I want to see what val looks like and see how val changes. So I've set the breakpoint, I hit run, and now we've gotten to that spot. So here we see val is declared and it's set to 0, and we can see up here that we have these local variables and val is actually set there. So now if I step over, which is going to step to the next line, you can see it stepped over 2 lines, or what appears to be 2 lines to us. That would be really kind of incorrect from the debug perspective. We want to step line by line. If I say step over something, I don't want it to go 2 or 3 lines or whatever. But the reason it's doing that is because this is an optimized build. And so things have been optimized out. And so there's not always a statement that it can correspond to based on where we are in the code. So for example, if I do this again and I step, notice what happens. I should have stepped down here to line 16 and then to 17 and so on, and all of a sudden I'm now at the end of the function, which I shouldn't have been just by stepping. And notice over here it says that my value, which is what I wanted to see, has been optimized out. So this is a product of the optimizer. So we can work around this. If we want to make sure that val sticks around, we can add the volatile keyword in front of this. What that will do is it will stop the debugger, it will stop the optimizer from optimizing that variable away. So I'm going to hit stop, and I'm going to put the device back in DFU mode. Okay. And then we're going to hit debug again. And we'll see the effect of changing that to volatile. Okay, so we're downloading again. Okay, so it hasn't updated our output here, but we know that we're not running, so we can hit run, and we are back to the original breakpoint we had before. We can hit run again. Now we're at this breakpoint, so let's step again. So if I step over, now notice that actually because val didn't get optimized out, this statement now exists as well. And so we can actually see that we read in a 0. We're going to shift it 8 bits to the left, which is still going to give us a 0. Now we're going to read another value. And notice that we now have a val of 84. And that's decimal. And we're looking for 54 hex. And so we can actually see if we step here. Now, again, we stepped away from going into the return. That's just due to the optimization. But you'll notice the val never went away, which is cool. So at least we can preserve our variables so that we can check them out by adding volatile in front of them. Okay, so let's stop this and let's create some more code to implement the functions that we need to implement. So what I want to do now is add some code in that is related to building the temperature for the registers. So one of the complexities in this is we have a temperature, let's say 25.3 degrees Celsius. We have to get it into a special format to put it into the 2 registers. And this is the code to do that. And believe me, I didn't write this correctly the first time. It took quite a bit of testing. But thankfully, I had the debugger to help me step through this. The other thing you'll notice is when we get a temperature in, it could be negative, and I wanted to take the absolute value of that. And it turns out ABS, absolute of temp, will end up giving you an integer in the end if you use it as the default. So what we're going to do is we're going to include the math library. And now down here, floating point absolute should be fine, which it is. So now we've got the function to do this. And the reason I've created it as a function is because we actually have to use it several times. So for example, when we set the lower temp in our boundary condition, we're going to call the build temperature for registers, which is this function right here. And then when we do the set the upper temp, we're going to do the same thing. And when we set the critical temp, we're going to do the same thing. So this is sort of making our code dry in the sense that we're going to reuse that function again and again. Now, there are some other things that we're doing here that are repeating as well. So when we finish this library, I'll go back with another pass and sort of dry it up a little more so that we don't have code repeating like we're repeating here. But basically what this does is it gets the temperature and then creates an MSB and LSB from it, and then it starts a transmission. It tells it that it wants to talk to the lower temp register, sends those values, and ends. And when we do upper temp and critical temp, we're basically doing the same thing to those, and that's actually how we're setting these. And then finally, there's the setting an alert. So with this code, we do the same kind of thing at the beginning. And then what we're doing is if they've enabled the alert, we say, okay, if enabled, then we have to determine whether we're active high or active low. And so if we're active high, we're ORing or setting the appropriate bit. If we're active low, then we're clearing the bit. Okay, so we're taking that mask, knotting it, and then doing the and. And then here, we're just setting the bit for the alert control to turn it on. So how would you know to do all of this stuff that I am doing? Well, the way you're going to do that is by going to the datasheet. So for example, here in the datasheet, I've taken a shot out of there, and I'm showing that the upper bound is register 2, and this is showing the format of the data that needs to go in there. And of course, here's the lower bound at 3, and here's the critical temp bound at 4. So I'm using the datasheet to determine that I needed to create these items here and write them out to set those limits. Then finally, the configuration register is where we're going to actually turn this alert on and off. So for example, here on bit 1 is the alert polarity, and bit 3 is going to be the alert control. And I can actually see those two there, and then the status is where I can read this and find out if the alert's been asserted or not. And that's what this code is doing right here. Okay, so it's setting the proper bits and then writing them out to the configuration register. And then finally, to complete this implementation, I'm going to want to do the get temp, which is basically the ambient temperature register, and I'm going to get the values from there, and then I'm going to sort of do the reverse and actually create a floating point temperature reading from those values. And then finally, we want to add in the ability to get the alert status, which will tell us if we are actually in an alert condition or not. And again, this code here is reading this register right here. So let's just see if this builds. So we put a lot of code in there. And it built just fine. So that's a good sign. So what we want to do now is go back to our code here and exercise some of this stuff. So what I'm going to do is go here and we will paste in this code. And what this code is doing is it's starting out and it's reading a temperature. So we get a temperature value, whatever it is. And then we're setting the upper limit to be 1 degree above and the lower limit to be 1 degree below of that current temperature. And we're setting the critical temperature at 40 degrees Celsius just because we're going to put it at some high value. And then we're actually going to turn the alert on with a true here. And we want the alert to be normally high and then the alert pin go low when an alert actually happens. And then finally, we can, in our loop, use serial to write out a high or low status and a current temperature reading so we can see if all of this is really working well. And of course, we're going to need to do a serial.begin here to make this work properly. All right, so one final, let's see if this builds. And it builds great. Okay, so I'm going to put this back into DFU mode. So the tricky part with getting into DFU mode is that I have to hit the reset button on the Xenon so that then this trick takes place. And that's because we're using the debugger in tandem with this. Normally you don't have to do that if you're not using the debugger. But again, that's something that I think over time will get fixed. So we'll go ahead and we are in DFU mode. We'll go ahead and click debug. And it will start downloading here in a second. All right, and let's see if it works. All right, so we've run to our first breakpoint and notice that we didn't make temp volatile. And so look over here, temp says optimized out. Now we're going to find out what temp really is after we step into this function. So if we go into set upper temp, I've set a breakpoint here. So as soon as we come in, we should see the value being passed in here. And then we're going to build up our registers for a upper limit and then set them here. And we'll do that for lower and critical. And let's give this a try and see if it all works. So we'll run to the next breakpoint. So here we are. We're now inside set upper temp. And we see a temp of 26.93. So basically, when we heat up our environment for the temp sensor, it should have to exceed this. So it should have to get to about 27 degrees before our alarm goes off. So let's go ahead and let it rip. And what we're going to do is our cool term here. Say connect. All right, so we're showing 25.56 right now as our temperature. So let's go ahead and grab our heat gun, and all I'm going to do is bring it in enough to kind of raise the temperature a little bit. And once we get above our threshold, there we go. We just got above it. Notice now our LED went off, and that's because we have it set so that the high of the alert is normal and it goes low. That's its polarity for when an alert is occurring. Now what we're seeing on the screen is actually a high and a low, not based on the pin, but based on the fact that high is an alert, low is no alert. So that will always be the same. But the polarity of the pin itself can be swapped, and we just saw that.